So everyone who is watching, welcome to our presentation, to our seminar today. And our speaker is Dr. Yann Mairesse from the CNRS Bordeaux at CELIA. And it is quite interesting because it's going to be the second talk about chirality. And he generated his first and second pulse in 2000 as a summer student in CELIA, but he didn't realize it because at the time there was no way to characterize attosecond pulses. But wow, this is cool. You know, you can even say, I went there, I was a summer student, and then I measured one and generated it. So soon after the first attosecond measurements in 2001, he started his PhD thesis in Bertrand Carré's group in CELIA on the generation, characterization, and optimization of attosecond pulses. He and his colleagues used the emerging rabbit technique to measure the chirp of attosecond pulses in a train, transpose the spider technique to characterize the femtosecond profile of high harmonics, and they introduced also the frog crab method, which enables the complete characterization of arbitrary attosecond pulses. So we had a lot of animals. We had frogs, spiders, and rabbits. And it's really good. We also have cats in the seminar logo, so it fits into the theme. And these are very powerful measurement techniques if you don't know, for those who are not familiar with the field. And then Yann moved to Ottawa in 2005 as a postdoc in Paul Corco's group to work on high harmonic spectroscopy of aligned molecules. And they fully characterized the high harmonic emission, everything, amplitude, polarization, phase, and established that several molecular orbitals could contribute to high order harmonic generation. And this then could reveal the underlying attosecond dynamics. And he went back to France in 2007 and settled at CELIA in a research group combining experimentalists and theoreticians. And since then, they have been investigating the strong field response and ultra-fast dynamics of increasingly complex systems, atoms, atomic molecules, polyatomics, clusters, etc. So getting more and more complex. And in the past few years, molecular chirality has become their main subject of interest. And they have used multiple approaches to investigate the femtosecond and subfemtosecond dynamics of chiral molecules, from chiral high harmonic generation to time-resolved photoelectron circular dichroism. And they have used strong field spectroscopy to measure the attosecond dynamics underlying chiral photoionization and to control the chiroptical interaction by tailoring the instantaneous chirality of light. And you can see from the picture he sent to our gallery that he also likes hiking, like our speaker last week. And he's going to talk about the influence of molecular chirality on tunnel-ionization dynamics. So we're ready to go when you are, Yann. Thank you for accepting the invitation.
Okay, thanks a lot for the introduction. Thanks for the invitation. So do you see my screen share now? Yes? Okay. So yes, I will talk about the influence of molecular chirality on the dynamics of tunnel-ionization. So it's a rather large project. We started the experiment, I guess, in 2017, something like this. And we only got to the final understanding recently. The experiments were done in Bordeaux, and we also have a lot of theoretical input, which was necessary to understand this. And the theory is also done in our group, which is a mixed group, as Carla said. And we collaborated with the Weissman and SCPMR groups on the experimental aspects. So we are interested in strong field physics. And in general, when you use a strong laser field to ionize molecules, there's a series of ultrafast processes which can occur and which can be used to retrieve information on the molecular structure. So it is reviewed, for example, in this paper here, you can do self-imaging of a molecule by its own electrons. So there are different processes which can happen depending on the time at which the electrons are released within the oscillation of the strong laser field. But all of these processes share the same first step, which is tunnel ionization. So the primary process, tunnel ionization, can be described schematically like this. You have a Coulomb potential, which is bent by a strong laser field here. And so the strong laser field lowers the barrier such that part of the electrons can tunnel out into the continuum. And so we have this process which can be seen in two steps, let's say. You have first, in the classically forbidden region, you have tunneling which occurs. And then in step 2, the electron is free. It's like in the continuum, and it can be accelerated by the laser field. So one question which arises if one aims at doing molecular spectroscopy based on this primary process is, what is the structural sensitivity of this process? And so there are different theoretical approaches to describe this, which are very successful. And so the first approximation is the strong field approximation, in which you neglect the influence of the ionic potential after tunneling. So this means that you consider that once the electron is here, it is purely driven by the strong field. Now, you can add corrections to this. There are various ways of doing this. Coulomb corrected strong field approximation, in which you add a correction along the electron trajectories here in the second step. But you can also Coulomb correct the first step here. There is actually an influence of the Coulomb potential in the sub-barrier process, and it can cause a phase shift of the emerging wave packet. So this means that this primary tunneling process can imprint a phase. The potential imprints a phase, as shown in this paper here. And all of these different methods are nicely reviewed in this second paper. So the question is, if we have this phase which can appear in the tunnel ionization step, how can we probe these kind of things? So we need an unambiguous signature of the interaction with the ionic potential. And the way we chose to achieve this is to ionize chiral molecules with a rotating laser field. So our target will be chiral molecules. And chiral molecules, as you know, exist as two forms, which are mirror images of each other, like the two hands, and they are called enantiomers. When chiral molecules interact with circularly polarized light, there is a variety of processes which can happen. And the process we will use, the signal we will rely on, is photoelectron circular dichroism. So here is a typical photoelectron circular dichroism experiment. You start from randomly oriented enantiopure chiral molecules, and you ionize them with circularly polarized radiation. As a result of ionization, there are electrons which are ejected, and you use electrodes to, for example, project the momentum distribution of the electrons onto a detector. So this would be velocity map imaging. And you measure, by doing this, the projection of the angular distribution of the electrons. Sorry, this is a typo. So if you do this in chiral molecules, you see this very interesting effect, which is that if you use, for example, left-handed light to ionize a certain species, you will have more electrons ejected forward. And if you use right-handed light, you will have more electrons ejected backwards. And so you can think of this really in an analogy with a nut and bolt, where you have a rotation motion of the nut, which and the thread converts this rotation into a translation, which depends on the handedness of the thread and on the rotation direction. So in this type of experiment, the signal is going to be, for example, so it's the asymmetry here, the forward-backward asymmetry, and you can get it by comparing the response of left and right polarization, and you obtain this photoelectron circular dichroism. So it's a signal which is from negative to positive. It's forward-backward antisymmetric with respect to the direction of the propagation of light. So what is very interesting for us is that this is a pure electric dipole effect, and so it is strong. In general, chiroptical processes produce quite weak signal, and so this process here is much stronger than most other circular dichroisms. I'm not sure this is up to date, but let's say you can measure several tenths of % in this asymmetry here. And so in this talk, we will be looking basically at forward-backward asymmetries resulting from strong field processes in chiral molecules. And the idea is that this is a background-free signal in the sense that if you don't use chirality, if you do not introduce chirality in the dipole approximation, your distribution is purely forward-backward symmetric. So if you see forward-backward asymmetries, they are the signature of chirality and thus of the role of the ionic potential. So what is the origin of the PECD? It can really be described as resulting from the scattering phase of the outgoing electrons in the chiral potential. So you have these electrons which are ionized by absorption, for example, of one X-ray photon. And you can show that by decomposing the outgoing wave function in partial waves, that the PECD is going to be proportional to the sign of the relative phase between adjacent partial waves. So the message here is that it is very sensitive to small phase shift in the scattering and very sensitive probe of molecular chirality. You can also see PECD purely classically. You can actually take electrons in a classical potential, and you place these electrons in a rotating laser field under the influence of the potential. And this is, for example, a classical trajectory calculated by CTMC. And as a result, if you do this purely classically, you will end up with more electrons forward than backward, even after averaging over all the orientation. So what about the chiral sensitivity of strong field ionization? So we've described strong field ionization here as a two-step process. And so within the strong field approximation, there should be no PECD because there's no influence of the chiral potential. But now it was shown that if you include a correction in the continuum, then you can get a PECD effect. And so basically, this means that you have the scattering of the chiral potential here once the electron is in the continuum, which imprints a phase and amplitude asymmetry in the photoelectron-angular distribution. But on the other hand, you could argue that if the electron here emerges far away from the core, then the influence of the potential vanishes. It could be very low. And so one question which arises is, could there be a chiral sensitivity here of the first step? Is there an influence of chirality on the wave packet emerging from the tunnel? So this is the question we'll try to address today. So in the end, it comes down to measuring strong field ionization dynamics. And to measure strong field ionization dynamics, there's a number of techniques which are well established in the attosecond community. So there's rabbit measurements, Atto clock, photoelectron interferometry. And with these techniques, you get different information. So for example, with rabbit-like measurements, you can access the photoionization delays. So the delays at which electrons emerge from an atom or a molecule. If you do the Atto clock measurement, you will use a rotating laser field to induce angular streaking. We're going to discuss this in just a few minutes, so I won't go into more details. And if you do photoelectron interferometry, this is an interesting technique because you can measure the relative phase between the packets through interference. And so you can, for example, reveal the existence of a sub-barrier phase, as done here in this paper. So now what happens if you look at chiral molecules instead of looking at atoms? Well, you can do rabbit measurements in chiral molecules, and you can observe that there is actually a chiral-sensitive delay of a few attoseconds between ejection of one enantiomer and its mirror image. You can also do chiral Atto clock measurements in chiral molecules, and you will observe forward-backwards asymmetry of the angular streaking, as we will see. This is one of the two techniques we will use. Now, for photoelectron interferometry, it might seem a bit more tricky because if you use circularly polarized laser field, you don't really get interference structures. So we will see how this can be solved. So this is the outline of the talk. We will first look at chiral Atto clock measurements, and then we will see how we can perform interferometric measurements through the subcycle gated chiral photoelectron interferometry. This is not an acronym, don't try to pronounce it. The Atto clock. I will briefly describe the principle. The principle of the Atto clock is to use an elliptically polarized field to ionize a target, say an atom. So the electric field is in red here, and it releases around its maximum an electron wave packet. Now, because the field rotates in time, the electron wave packet is streaked angularly, and as a result, you will end up by measuring photoelectronic angular distribution, which points in a direction which is different from the laser field main axis here. And actually, if you do the strong field approximation, you can show that the final momentum here is dictated by the vector potential at the time of ionization, such that in this configuration with a vertical ellipse, you would expect the electrons to end up along the horizontal x-axis. So the principle of the Atto clock is to look at this distribution and see if there could be some offsets of these angular distributions. And basically, one reason why there could be an offset is if there was a tunneling time to go through the barrier. So let's say that you launch electrons here when the field is maximum inside the barrier, but the electrons emerge at a certain time after. So when they emerge in the continuum, they see a vector potential which is rotated. And so you will have an angle here in this Atto clock. Another effect which can produce offset in the angular streaking is the influence of long-range potential. Actually, even if the electron starts here when the field is maximum, you can show that the influence of the Coulombic potential during the electron acceleration in the continuum is going to imprint an additional offset to the Atto clock rotation. And so you will end up with a delay here. So recently there's been theoretical and experimental work which has demonstrated that this was the dominant effect in the Atto clock, such that the Atto clock is primarily a probe of the influence of the ionic potential in the electron angular streaking. So in our experiments and calculations, we will use bicircular fields. So this means we will use a laser field, which is constituted of a superposition of a fundamental and second harmonic. So they are described here, both as circularly polarized. So you have a fundamental field omega here, which is circularly polarized. And you have here a fundamental field, a second harmonic field with a ratio R. These bicircular fields are very versatile, and it's been shown in the Atto Fridays seminar by Dejan Milosevic that you could do a lot of strong field physics control with such fields. These are two examples. And here we will use co-rotating bicircular fields, which look like this. So basically, this means in our Atto clock experiment, instead of having this elliptical field, we will use this field, which is constituted of two co-rotating fields. So it looks like a bit of a reversed heart shape. It maximizes here at the top, and the vector potential, which is in dashed, when the field points here, the vector potential maximizes here. Now, the fact that you can do Atto clock measurements with more complex fields than elliptical was demonstrated in these theory works with different configurations. And here we will rely on this. So the principle is that we will use the rotation of the electric field to angularly streak the electrons and detect the offsets in the angular distributions here. So the experimental setup is here. Basically, we start from a 1 kilohertz laser, 25 femtosecond. We split it in two. It's a Mach-Zehnder interferometer. And so we frequency double one arm. We recombine the omega arm and the 2 omega arm, and we take care of the polarization states with quarter wave plates. Our target molecules will be camphor and fanchon, which are isomers. You see they differ only by the position of these two methyl groups here. And they have rather low ionization potentials compared to what we are used to in strong field physics. I mean, it's not rare gases, right? We are not in the 10 or 15 eV range. We are in the 8, 9 eV range. So keep this in mind when you see the laser intensity we use. And our detector will be a velocity map imaging spectrometer. We've seen this before. It records 2D projections of the 3D distribution. And so actually, this is a bit of a problem because in the Atto clock, we want to record the 3D distribution, but there's a simple way around this is to do tomographic reconstruction. So that's what we do. I mean, I can give details if needed. So as a result, this was the principal figure I showed you before, and this is what we observed. So this is a measurement of the photoelectron angular distribution from camphor molecules. And this is a cut of the measurement in the laser polarization plane. So I define the axis here. Light propagates along the z-axis, and the bicircular field is in the xy plane, okay? So what we're looking here is really in the Atto clock plane, basically. So you see that the distribution is constituted of several peaks in the photoelectron angular distribution, and they are above threshold ionization peaks. So we will call this one ATI1, which is the first peak appearing in the continuum. And you see that it maximizes angularly at a certain angle here. So this is the Atto clock offset angle for the first ATI peak, which we define as phi 0 here. So this is the phi 0 of the first peak. If we look at the next ATI peak, we see that it has a lower, if this is 0, we have a lower streaking angle. And the third one has even lower. So the Atto clock angle phi 0 depends on the ATI peak, which means it depends on the kinetic energy of the electron. Now, if we want to look at the chiral sensitivity of the signal, we need to look at the 3D distribution and compare what happens to electrons which are ejected forward and backward with respect to the light propagation axis. So we're going to compare the Atto clock signal of electrons ejected at a certain angle theta here or minus theta on the other way. So theta positive will mean forward ejection. Theta equals 0 means ejection in this plane here. And theta negative means backward ejection with respect to the light propagation axis. So let's measure now for each theta. We look at this 2D distribution and we measure the angle at which the ATI peak maximizes, and this is what we get. So in the theta equals 0, we get what we see here already. The first ATI peak is offset by about 55 degrees with respect to the higher one. So this is ATI 1, 2, 3, 4, 5. And as the energy of the electron increases, the angle here gets smaller. We see that there's a variation of the angle, of the Atto clock angle along the ejection angle, which means that forward electrons are ejected at a different Atto clock angle and backward electrons. You see there's an offset here of 10 degrees between the ejection of forward and backward electrons. And so this is a dichroic signal, this is a chiroptical signal. So to extract it, we're going to differentiate the forward and backward Atto clock angles to get this delta phi forward backward, which is the difference between forward and backward streaking angle. So it's the chiral Atto clock asymmetry. And you see that for the first ATI peak, there's a very strong asymmetry. And now for the next ATI peaks, they all behave pretty much similarly. So we have an increase here of the Atto clock, a linear slope, basically, of the chiral Atto clock asymmetry. So what does this mean? This means that the Atto clock is sensitive to chirality. This quantity here would reverse if we switch the laser helicity, or if we switch the enantiomer. We just like reverse the sign of this. And we have a very similar behavior for the ATI peaks 2, 3, 4, 5. ATI 1 is very different. So now there's another observable we can look at. It's the number of electrons. It's the basic observable related to PECD that I described at the beginning. I said, okay, if we use circular polarization, there's going to be more electrons ejected backward or forward. So we can measure this in this measurement also. So what we do is we integrate the number of electrons in the ATI peak ejected at a certain angle, and we look at the forward-backward asymmetry in the number of electrons. So this is related to the PECD. And so I will call this the chiral asymmetric yield. It's the difference between signal ejected forward-backward. So it varies a lot. We see again a different behavior between the first ATI peak and then the next ATI peak. It basically changes sign. But what is striking is that we see that as we increase the order of the ATI peak, which means as we increase the kinetic energy of the electron, the chiral asymmetry increases, and it reaches about 2.5% here. So in a way, this is a bit counterintuitive, because in general, in multiphoton ionization, we are used to seeing that the chiral sensitivity decreases when you increase the ATI peaks. I mean, hand wavily, it means that the higher ATIs are better described by plane waves, let's say, so there's less chiral sensitivity. So maybe this is not really, maybe this is because of the structure of function of Kaempfer. So we would like to check how general this is, and we compare now the measurements to the other molecule we studied, which is function. And so here are the results. So the results are actually, I just blink like this, they are actually pretty similar. So we have a similar behavior of the overall Atto clock. We have a weaker chiral response. Basically, the chiral Atto clock shows a 0 signal only for the first ATI peak, but then the 2, 3, 4, 5 ATIs are like around 0 here, really. On the other hand, we observe a strong chiral sensitivity of the measurement because the electron yield is forward-backward asymmetric. It's weaker, it's about 0.7%, but still it's significant. And so what is striking is, especially for high energy electrons, like the ATI5, we observe no chiral Atto clock shift, but we observe a strong asymmetry in the electron yield, in the number of electrons ejected forward and backward. So they are strict similarly, but there's not the same number of electrons. So how can we interpret this? The issue is that, and this was what we discussed at the very beginning, there are 2 steps in the process. And so it's difficult to know, if we want to know what is the part which comes from tunnel ionization or under the barrier dynamics, it's difficult to decouple it from the post tunneling dynamics. So luckily, there's a way to decouple these 2 steps, at least in theory. And it was introduced in this paper. The idea is to compare a calculation in which you have a Coulomb potential in black. So this is the case we've presented from the start. And you compare this calculation to the same Atto clock calculation, but you use a screen potential, a Yukawa potential. And so you see that the screen potential, as long as you go a bit away from the core, the screen potential follows exactly the potential imposed by the laser field. So it's a very short range potential. So in this short range potential, you expect to have no influence of the potential here once the electron is in the continuum. So you would expect to have no influence of the step 2 in the Atto clock. So what are the results? This is the Coulomb potential calculation, which show clearly an Atto clock shift. You see that the distribution is rotated with respect to the 0. But if you now screen the long range potential, you see that the distribution gets here aligned perfectly with 0, which means that there is no Atto clock delay here. So what these results show is that the Atto clock shift is a long range effect. So if you kill the long range potential, you kill the Atto clock rotation. Now, how does this play a role in the photoionization of chiral molecules? So to determine this, our theoretician colleagues did calculations using a toy model chiral molecule, which is called the Bernardine, because it's Bernard Pons who did the calculation. And it's a toy model molecule with 4 centers, which are here, and 1 electron. And so Bernard uses this to do TDSE calculations. So he calculates the photoelectron angular distribution like we would do, like we measure in the experiment. And the first thing is we can compare, in his calculation, he can do 2 things. He can take the initial potential, like the full molecular potential, or he can add a Yukawa term to screen the potential, like what was done in the previous paper. And so the idea is going to be to compare the response of a full Bernardine molecule and a screen molecule in the TDSE, and to see if what we can learn from this. So, okay, here are the photoelectron angular distributions calculated and measured. So this is the measurement in Kaempfer. We've seen it before with the ATI peaks. This is the measurement in function. It really resembles the Kaempfer one. And this is the TDSE calculation with the full chiral potential of the molecule. So the first thing is, despite the simplicity of the molecule, which is basically 4 atoms, you see that the overall trends are well reproduced. This first ATI peak here points to around here, like the 2 others. And as you increase the order of the ATI peak, the Atto clock angle gets closer to 0 here. So we would say that the fact that we observe similar Atto clock shifts in camphor, Fanchon, and TDSE sort of validates the TDSE model and tells us that, of course, we don't expect quantitative agreement, but it tells us that it describes something which is not far from reality, the experimental reality. Now, what happens if you screen the potential in the TDSE calculation? Well, you see that the Atto clock angle vanishes and the peaks get aligned here around 0. Okay, so now this is a qualitative picture of it. So let's do the same analysis as we did for the experiment, but let's conduct it on the theory calculation. And let's look also at the chiral response. We will start with the calculation using the initial potential to the full chiral potential. So this is the Atto clock shift obtained for ATI 1, 2, 3, and 4 from the calculation to be compared to what we had measured in camphor. And so basically there's a good qualitative agreement. We observe the same trends as in the experiment. Now we can look at the chiral response, which is most interesting to us. So we look at the asymmetry here of this Atto clock. So we observe that at 40 degrees, there is a -3 degrees offset of electrons ejected forward with respect to electrons ejected backward for the ATI peak 2. On average here, we observe shifts of about 2 to 3 degrees for the ATI peaks. And this is the same order of magnitude as what we had observed in camphor, except for the first ATI peak, which was like anomalous in camphor. Now, if we look at the chiral asymmetry, so the PECD, let's say briefly, so the asymmetry in the number of ejected electrons, again, we observe something which resembles the experiment, where we have an opposite behavior of ATI1, and then the other ATI peaks show a rather large signal of 2%, even for the higher ATI peaks. Okay, so again, this tells us that our model is not too far from reality. But now let's see what happens if we screen the long-range potential. So now we force the chirality to only play a role at short range. So when we do this, we find that the Atto clock shift vanishes, it gets close to 0. And so the Atto clock shift is canceled by screening, as shown before in the Torlina paper that we've discussed. Now, the chiral response is interesting. You see that if you look at the asymmetry of the Atto clock, for the first ATI peak, you have an asymmetry. The second one, a lower one. And then the asymmetry vanishes for higher ATI peaks. For ATI 4, there is basically no more chiral asymmetry in the Atto clock streaking. So it means that if you reach high enough energy on the electron, you can cancel the chiral Atto clock asymmetry. So the screening is efficient. The screening of the chiral potential is efficient, but it's efficient for high energy electrons. For low energy electrons, there is the screening is less effective, and you still observe some influence of the chirality. Now, the fact that at high energy electrons you observe no asymmetry of the Atto clock tells you that there's basically no chiral tunneling delay in the calculation. And now let's look at the last part, which is the asymmetry in the number of electrons. Because right now what you could say is, okay, you screen the chiral potential, and so basically chiral effects disappear. And here you have the result which show that no, this is not what happens. Even if you screen the chiral potential, you see that the asymmetry in the number of ejected electrons remains strong. Like for the ATI peak 4, you still have a 3% asymmetry, which is comparable to what you had without screening the potential. And so this means that you have screened the long-range potential, but you still have a very strong asymmetric forward-backward asymmetric signal. So for high-energy electrons, you have no Atto clock chiral asymmetry. but you have a strong asymmetry in the electron yield despite the screening. And so this is a remarkable result. So what does it show? What does it mean? We have seen that there's no Atto-Chiral asymmetry for this high ATI peak. So this means that step 2 has been, the influence of the ionic potential in step 2 is cancelled by the screening. There's no chiral influence of the chirality in step 2. Nevertheless, we observe a strong asymmetry in the electron yield. And so we conclude that this strong asymmetry results from the first step, which means the sub-barrier dynamics can induce a chiral response. It can induce an amplitude asymmetry at the exit of the tunnel, and it is imprinted by the chiral potential under the barrier here during the tunneling. We also observe that we do not detect a significant tunneling time in the calculation. So we have here a first result, which tells us that actually pure tunneling dynamics can produce sensitivity to chirality. And the wave packet here is modulated by the chiral potential. Now, one may wonder if this first step could not also induce a sub-barrier chiral phase on the wave packet. So we would like to detect this phase. So the question is, can we resolve the phase properties of the wave packet at the exit of the tunnel? And if you want to measure phase, you need an interferometer. And luckily, interference is ubiquitous in strong field ionization, as nicely reviewed in this paper. I mean, it's all about phases. So this means we should find a way to measure them by looking at the distribution in photoelectron imaging. And so this is the second part of the talk, which is subcycle gated chiral photoelectron interferometry. So yeah, the first term is interferometry. Let's see already how to get an interferometer, and then we'll discuss how to do subcycle gating. The most basic interferometer that you can find is actually naturally built in the above threshold ionization process. It's built by the periodicity of the threshold of the ATI process. If you have a laser field like this, and you have basically ionization when the laser field is strong enough. But this ionization process is going to release different families of electrons. You have direct electrons, which are ejected here between the 0 of the field and the maximum of the field. So for example, this here is a direct electrons. And these direct electrons are going to directly escape the ion. Here you have another ejection of direct electrons. And this result, these direct electrons within the strong field approximation, they result in this kind of angular distribution. But you can also have ionization as on the trailing edge of the field between the maxima and the 0 of the field. And these electrons have different trajectories. They are indirect. They can go in one direction and get back and be driven back so they wiggle around before escaping. And so, but they show the exact same momentum distribution within the strong field approximation. And so if now you superpose these, because that's what the experiment does, you end up with interference between direct and indirect electrons. And so these are intracycle interference. So it's one of the most basic interference in ATI, but it's often hidden by other processes. I just want to say that whenever I have to draw these, I go to Manfred's line simulator online, because otherwise I always do mistakes. And it's really a great tool to develop some intuition on how strong field ionization works. So how can we observe these? The problem is if you do the experiment, as done by the Frankfurt group here, this is what you measure. And so you would expect to observe something like these, bows like this, discretized by ATI peaks. And actually what you see is mostly a spider. You see this spider structure here. And so this spider structure, which is certainly interesting, involves rescattering electrons, and it basically dominates the response. And this is not what we want. We would like to have a simple signal coming from simple intracycle interference. So I also mentioned that not only can you have a spider in your spectrum, but apparently you can also have cats, which is even worse. And I mean, I don't know how to handle that, really. So luckily, one solution is to use two-color laser field. So you still have your strong infrared laser field, and you plug in an orthogonal polarization component. And so it's shown in this paper that if you do this, basically, this perpendicular component is going to drive the electron sideways, and it enables you to reveal here the interference. You see here, these are the fringes we're looking for. Okay. So actually, orthogonal two-color laser fields are another important component of strong field physics, as also shown by Dejean in his talk, and as, for example, exemplified here in a few papers. And so in our case, what we will do is we will use a combination of fundamental and orthogonally polarized second harmonic. And this is the kind of field it produces, depending on the phase phi, which is phi omega to omega between the two components. So let's go slowly, and let's first look at the first case here. We have the electric field, which oscillates in time, and it describes an H shape. Okay, so this means it rotates here counterclockwise, then clockwise, then counterclockwise, etc. The vector potential associated with this field describes a C shape. Okay. Now, if we change the phase, the relative phase between the two components, instead of pi over 2, we put pi. Now the electric field describes a C shape, and the vector potential describes a H shape. Okay, so this means that by playing with this phase, we can play with the shape of the field. Now, these two-color fields still produce nice interference patterns, as shown by the previous experiment, and the direct electrons produce basically a wave packet whose shape is determined by the vector potential. We had said this before, right? The momentum distribution of electrons within the SFA follows the shape of the vector potential. So if you use an 8-field shape, the vector potential is a C, and you get a distribution which is a C. Now, the indirect electrons have the same distribution. And so these two are interfere, and this is our interferometer. Okay, so we have found our interferometer. Now the question is it sensitive to chirality? And so, I mean, a bilinear laser field, orthogonally polarized laser field, certainly have a chiral aspect because they rotate in time, right? But the field rotation reverses every half cycle. So can you really do something with this? First, you can quantify this field rotation by introducing the instantaneous chirality. So it's defined here, and it's basically the rotation speed of the field. And it is described as a color scale here that I've shown on all the plots. So this means here negative instantaneous chirality, positive, negative. So whenever you switch from blue to red, it means your field rotation changes sign. Usually, chiral light matter interaction uses circular polarized light or elliptically polarized light. And so the question is, can a field with a zero net chirality, because this one rotates, it cancels out on one optical cycle, can a field with a zero chirality produce a chiroptical signal? So a first answer to this question was provided in this theory paper in the perturbative regime, and it showed that there could be a chiroptical signal. And so what we will do here is study this in the strong field regime in this paper, and this slide is just devoted to showing the acronym describing the technique, which is enantiosensitive subcycle antisymmetric response gated by orthogonal two-color laser field, escargot, snail in French, chiral species. A great acronym found by Shaked Rosen. So we will see that this is meaningful actually, and that the subcycle gating plays a huge role in what we're doing. So what is this signal? I will not go into details of the experimental setup. I would simply mention one fact. The previous experiment I showed you were done with a TISAFS laser at 1 kilohertz. These experiments were done with a ytterbium fiber laser, and the main difference is the repetition rate. We use here a repetition rate of 700 kilohertz. And so this enables us to get high signal to noise ratio and reveal structures that would be difficult to measure maybe at 1 kilohertz. So this here is measurements in Fanchon, so 750 kilohertz rep rate for the laser. And this is the photoelectron angular distribution from Fanchon. So let's look again at the symmetry. This is the light propagation direction. And we are now looking at VMI images. So this means they are images in the PY, PZ plane. They are projection of the distribution. So this is the light propagation axis. And this is the polarization direction of the fundamental field. So we see that they are above threshold ionization peaks. And now if we want to extract the chiroptical signal, we need to measure the forward-backward asymmetry of the image. So we look at the difference between electrons ejected forward and backward. And this is what we obtained. So this is a forward-backward asymmetry of the signal. You see that it ranges about 0.5%. So it's a low chiral signal. And it's very sensitive to the shape of the field. If you ionize with the C-shaped field, you get this pattern. If you ionize with an H-shaped field, you get this pattern. Interestingly, you can see that the chiroptical signal is up-down antisymmetric, and it reflects the symmetry of your field. The instantaneous chirality reverses between up and down, so you get a chiral signal which reverses between up and down. Now, what can we do with this? Well, we can compare it to Bernardin calculations, so TDSE calculations, and we see that we get a rather reasonable agreement on the general structures. The order of magnitude, it's twice stronger here. In particular, we observe that when we use an H-shaped field, we have some sort of fringe pattern which appears in both the chiral signal from the Bernardin and from Fenchel. And this is the signature of the interference we're looking for. Now, unfortunately, recording the interference properly would require measuring in the light polarization plane, as shown here, right? This is where the interference is. And when we do VMI measurements, we measure in this projection plane here. And on this experiment, we were unable to do the 3D tomography at high intensity. So in the following, we will rely on calculations to draw the conclusion. So our goal will be to resolve the tunneling phase. For this, we will start directly from the case where we screen the molecular potential with the Yukawa screening. We increase the intensity to 510 to 13 watt per square centimeters to reach a Keldysh parameter of 1. This is, I think, the highest that could be converged in the calculation. And we look at what the photoelectron momentum distribution looks like, and it looks like a beautiful interference pattern. So this is in the laser polarization plane, the distribution from the TDSE with the screening. If we compare it to SFA, we find a very good agreement. So this means that the screening is efficient and that we can basically neglect the influence of the potential in the second step here. Now, the main question is, how can we resolve the chiral signal? And how will the instantaneous chirality of light play a role in this? And this is really not a trivial question at first. And so to develop an intuition on what could be the influence of the chirality in these two steps, we introduce a sort of chiral SFA model, sort of. So the idea of standard strong field approximation is that you get the electron momentum distribution by summing over the electron trajectories the exponential of the complex of the action accumulated by the electron. So basically, you have electrons which are released at different times, T0. They undergo some dynamics, and you integrate the action along these dynamics, and you sum this, you get the photoelectron momentum distribution. Now, what we do in this phenomenological chiral SFA is we introduce by hand an amplitude alpha and a phase beta modulation, which, so the amplitude is here, 1 plus alpha, the phase is here, and the phase. And these are supposed to mimic the chiral response. So let's go step by step through the results, the definition. They are defined here by a certain magnitude alpha 0. We plug in the sign of PZ because the chiral signal must be antisymmetric along the light propagation axis. So it must switch sign whether the electrons are ejected forward or backward, which is the sign of PZ. The chiral response is accumulated along the electron trajectories from the ionization to infinity, so we integrate it. Very importantly, it is weighted by the instantaneous chirality of light. And so that's where light, the fact that the instantaneous chirality of light varies in time, introduces a temporal gating. And last, of course, this must depend on the position of the electron. So if we want to mimic a chiral signal from step 1, we will assume that the response is instantaneous from tunneling. So we plug in this response function, a Dirac function. We say there's the chiral response only at the instant of ionization when T equals T0. On the other hand, if we want to mimic the chiral response in the acceleration in the continuum, it will be accumulated, but only once when the electron is close to the ionic core, right? Because the ionic core has a certain extension. So we're going to weight these signals by a Gaussian function, which describes, basically mimics the extension of the ionic core. And so we have a very simple model here to try to predict what could the chiral signal look like. So we calculate the P function and we calculate the forward-backward antisymmetry. And we look at what the different cases produce. So this is quite simple. We have the case where the electric field describes an 8, and we calculate the chiral signal in projected in the laser polarization plane here. So we see first that if we plug in an amplitude modulation in step 1, we have no signal, no chiral signal. Why is that? Well, it's because electrons ejected by from the direct and indirect families, they are ejected at opposite instantaneous chiralities. And so this means that if one electron has a positive modulation, the other one has a negative chiral response, and the two cancel out. On the other hand, if the instantaneous action of tunneling is now a phase shift, we observe a chiral response. Why? Because you shift one electron by a certain value, you shift the other electron by the opposite, such that when they interfere, you measure twice the phase shift. And so this means that if you have a sub-barrier phase, you can get a signal, a chiral signal. So you see that the idea is to try to distinguish the possible sources of chiral signal by looking at these 4 panels. And the issue here is that if you have a sub-barrier phase or a continuum phase, they produce pretty much similar signals. So it's not going to be very distinctive. So now if we switch the field configuration, instead of having an H-shaped field, we use the C-shaped field, it's much better. Because now our chiral SFA predicts very different signals, whether the signal is accumulated in the continuum along the electron acceleration or acquired sub-barrier instantaneously. And so this is actually quite good, because if we now compare to the TDSE calculation, we are able to identify which is contributing. And so this is the final result. We have here the distribution from the calculation in the screened chiral molecules. We will focus here on ATI peak 2. We will see the others after. And this is the chiral signal we observe. So it's the difference between electrons ejected forward and backward. So we see there's a forward-backward asymmetry in the screen molecules, and it's about 0.5%. So where is it accumulated? Now we compare to the chiral SFA. And we see clearly that this here resembles the continuum amplitude case. So this means that what dominates this chiral response here is the PECD accumulated in the reminiscent long-range chiral potential. It means that the screening of the Yukawa is not enough to completely kill the continuum chiral response. Now, if we switch to the C-shaped configuration, it's pretty interesting, because in this case, this is the TDSE SFA. We look at the ring here and we see that it shows many fringes. And so this points out towards a phase effect. And if we look at the symmetry of these phases, you see that they are antisymmetric left-right. You see it's blue, red, red, blue, blue, red. And so you can distinguish between a continuum phase and a sub-barrier phase just because of this symmetry property, which means that this response here in the TDSE from the screen molecule is acquired because of a sub-barrier phase. So we can do a quantitative analysis. We use these 4 contributions as a basis, and we use them to fit the chiral response of the different ATI peaks. And that's the final result. This is what we obtain. We resolve the phase and amplitude of the sub-barrier response in the chiral photoionization of Yukawa screened molecules. So we see that the screening is efficient in this case because we never observe really continuum contributions. And now we observe clearly sub-barrier amplitude modulation for the different ATI peaks, which ranges about 2%. And we observe a phase, which is about 20 milliradians. So the chiral signal is dominated by sub-barrier dynamics, thanks to the Yukawa screening. we have a 20 millirad chiral phase shift and a 2% amplitude modulation accumulated during what is here non-adiabatic tunneling. So here are the conclusions. The subbarrier dynamics introduce a chiral-optical response. In the Atto clock, we see no chiral tunneling delay, but we see a chiral subbarrier amplitude modulation. And the existence of this subbarrier amplitude modulation is confirmed by the interferometry scheme, where we see both an amplitude and a phase modulation in the subbarrier. There's sort of a contradiction here, because you could say that an instantaneous effect cannot be sensitive to the rotation of the electric field, right? Because if you want to know that the field has a certain helicity, you need to monitor its evolution in time. But now you could solve this contradiction by saying that the process is not instantaneous in the complex plane. And so there's a dynamics along the imaginary time axis in the whole description of these strong field processes. One important point is that our study lies in the non-adiabatic tunneling regime with a 1 Keldysh parameter, which means that the electron does not completely tunnel straight, but it actually acquires energy here during tunneling. So it gets excited, and this excitation process could be chirosensitive. So one important question is, what about adiabatic tunneling? Would it be a chirosensitive process? And we believe that it would be, because in this case, we could observe PECD from pure sensitivity of tunneling, because actually, even in a pure adiabatic picture, you can see tunneling as a quantum trajectory in which the electron explores the potential. So we believe that there should be a sensitivity of PECD in adiabatic tunneling from pure subbarrier contribution. Now, just very quickly, perspectives. So, I mean, it's a bit going back and forth between strong field spectroscopy and chirality. On the one hand, strong field spectroscopy is really great, and it's a versatile tool to study chiral dynamics. So bringing strong field spectroscopy to study chiral molecules is interesting. But on the other hand, chiral molecules are interesting for strong field spectroscopy because they provide background free sensitivity to the ionic potential. And so that's why we think that it is an interesting combination. Just a few words about work in progress. We are currently investigating the backscattered electrons, so the ones who go to 10 UP in chiral molecules. And I want to mention also that there are, of course, complementary strong field processes in chiral molecules. So there's chiral harmonic gyration, as reviewed by David recently here, and non-sequential double ionization, as shown here by this paper, which can produce huge chiroptical signals as well. I'm done. I'm sorry for the delay, and thank you for your attention.
So thank you very much for your really nice talk. I can see the questions are coming. So do feel free to put them in the chat or in the Q&A, preferentially in the Q&A. One announcement before we start, and it is that we have still a special issue of European Physical Journal D associated with the quantum battles. We are still accepting post-deadline contributions. So thank you all to those who have collaborated already. But if you still want to collaborate, do feel free to let us know. It's still possible. The issue is still open, and we are accepting reviews and tutorials as well. I'm clarifying this because many people have asked. So our first question is from Alexandra Landsman, and she's inquiring about Torlina et al. You mentioned Torlina et al. Nature Physics paper supporting the interpretation that tunneling is instantaneous. This suggests that the electrons appear at the tunnel exit at a time 0. However, the same paper finds negative, not 0, time values, direct quote from the paper. Across all intensities, we find the reconstructed ionization times are never positive. This is true, and if you look at the Torlina paper, the reconstructed tunneling times are negative, not exactly 0. This suggests that tunneling begins before the peak. Would tunneling before the peak affect your interpretation of tunneling chiral molecules?
Okay, so yes, this is absolutely correct. We try to focus on the phase and amplitude of the wave packet and not to focus on the tunneling times because it's a hotly debated subject and I'm a bit scared. The idea is that So you could debate, for example, this statement that when we observe, so what we say is that when we do the screening, we observe no chiral tunneling delay. So to agree, to go in the direction of Alexandra, what Alexandra is saying is that I cannot affirm this because I don't know when the electron entered the barrier, right? So it's correct that this statement is probably, I mean, I cannot affirm that there's no chiral tunneling delay because all I'm looking at is when the electron or where the electron arrives after the angular streaking. So I would not be too affirmative on this then. Sorry.
So feel free to continue the discussion. Is it okay with you, or would you like to pursue? Thank you. So she says it's fine with her, but do feel free to continue the discussion if you feel like it. And we have also from Manfred Line. Thank you, Yann, for the great talk. Can you remind me why you use the co-rotating bicircular?
Yeah, I didn't really say it. So we did, and actually it's like we did all these experiments with co-rotating and counter-rotating, did both. And so, for example, this beautiful distribution here is obviously from counter-rotating fields because it has a symmetry here with a threefold symmetry. So we did all the work with counter-rotating field and analyzing it and all. And then in the end, it turned out that we observed very strong interference effects in the signal. So there were a huge phase jump in this Atto clock signal, let's say, between the electrons. And this is really due to interference between the direct and indirect electrons. So then we thought that we should analyze the co-rotating case where we don't see this interference and that it's closer to, well, it's much easier to analyze. And so it's because of the field ratio that we had this interference. I mean, I know that it's not a problem in Manfred's paper, and it was shown, but in our case, we had clearly interferences. And so now that we have an understanding of the Atto clock effect and of the interferometry effect with the bilinear fields, it would be very interesting to go back to analyze the counter-rotating case in which the two effects should be combined and to try to rationalize the observations. So we have the theory, we have the experiment, we need to understand it. That's what I would say.
Would you like to pursue the question, Manfred? Would you like to? That's
fine, thank you very much.
Cheers, thank you. Another question we have is from Ivan Powys to all panelists and to Yann. In your Atto clock experiment, is the good semi-quantitative agreement between the Bernardin model and Kampfer and Fenchon rather surprising? Other chiroptical processes would clearly distinguish the three. So what can we infer about the apparently similar chirality of the three?
Yeah, so let's look at what is similar. What is similar here first is the non-chiral response. This is the photoelectron angular distribution. So they are similar, okay? And I would say this is because this is mostly driven by the ionization potential in a strong field picture. And so there is the scattering process in the continuum, which imposes the angular streaking delays. And so it's a strong field effect, which is sensitive to the long range potential, which must be similar in Fenchon, Kampfer, and Bernardin. Now, if we look at the chiral asymmetries, this is more puzzling. So what is very similar is the response here of, I would say, Kampfer and Bernardin, okay? But if we look at Fenchon, where is Fenchon? Okay, Fenchon is here. I'm sorry for the, Fenchon does not show the same weak Atto clock response in the Atto clock. It shows almost zero Atto clock, whereas Kampfer shows some Atto clock. So to be clear, what this shows is that the Atto clock is sensitive a bit to the potential, but what was surprising to me is that in the end, I get a much stronger response by looking at the number of ejected electrons, like the good old PECD, than by looking at the subtle effects of the angular streaking on the attosecond timescale. That's the first element of response. It seems like the integrated quantity can provide higher sensitivity. Now, if we compare Fenchon and Kampfer, we know that they should give very different PECDs. And here, the general trends, as I said, are pretty similar. So what we are wondering is, again, if this could be a signature of strong field effect. Basically, this here response, I think, contains a lot of the tunneling process. And I have no clue. I know that PECD is in general very sensitive to the structure, but I have no clue if the chiral response accumulated during under the barrier is that sensitive like this. I don't know. I simply cannot answer that. So I would say, yes, this is a bit surprising. In the strong field, you would expect to tend towards a universal response, but only from the long range scattering part. Now we're looking at short range effects, and we observe things which are pretty similar. So it's not spectroscopically, the signals are different, but it's true that we are used to seeing huge differences between camphor and fanchon, and here they behave pretty much similarly, and similarly to the Atto clock, which is a bit surprising. Yeah, I think that's all I can say. It would be nice to investigate the structural sensitivity of the first step of the subbarrier dynamics. Yeah.
So is this fine by you? You are allowed to speak if you would like to pursue the question. We have enabled it. So seems okay. So we have questions. There's some sound. Hi, it's okay. So we have also some questions from Chris Sparling. Thank you, Yann, great talk. You mentioned you could only recover full 3D momentum distributions using tomographic techniques. Does the symmetry of your elliptically omega to omega ionizing fields forbid the use of enabled transform P-basic treatment?
Yes, this is exactly the issue. It's like the symmetry prevents retrieving the 3D distribution from the projection. And so as soon as we put pulses which are not either linearly polarized or circularly polarized, so if you use elliptically polarized pulses, you cannot retrieve the distribution. And if you use two colors and all, or you cannot. So you need to do tomography, or you need to do 3D imaging using delay line anodes, which would record directly the 3D distribution. Or
is that okay?
Yeah, that's fine with me. That's perfect. Thank you.
Cheers, thank you. So we have also a question from Xiaozong Zhu. Thank you very, very much for the great work. The optical chirality of the C-shaped field looks always small. Could you explain a little bit why it can produce an obvious chiral signal?
Yeah, okay, so this C-shaped, so let's look at directly this basically. So first, the C-shaped field produces a weaker chiral signal compared to the H-shaped field, okay? Because it's the same scale on both. But I would say it really depends. So it's the chiral signal is the product, given our, like in the spirit of our hand waving chiral SFA explanation, it's the product of the optical chirality by the influence of the chiral potential. So it depends a lot on the electron trajectories, on what they look like. And so I would say that from the simulation we did with the chiral SFA, there's no obvious, we cannot have an obvious intuition on just by looking at the optical chirality as soon, like it's not because the optical chirality is twice lower, then we will not observe a strong chiral response, because it's really driven also by the electron dynamics, and it plays a large role. That's what I would say.
And we also have a second question, which is, besides, why do we need only to consider the instantaneous chirality of the light, as the electron is still driven by the field for some time? Thank you.
Okay, so I guess maybe a way, if I'm not sure I understand it. Maybe a way to reformulate the question would be, is it the optical chirality of light which matters, or the electron trajectory, or something like this? What I can say is this is something we looked at, because we're wondering if the chiral signal is driven by the chirality of the field or by the chirality of the electron trajectory. So basically by the angular momentum acquired by the electron. And if we plug in the angular, the chirality of the electron trajectories, it doesn't work at all. It doesn't look at all like what we observe. So this, we were happy because it also comforted us in the fact that it's the chirality of the light field which drives the process.
Mm-hmm. Mm-hmm. Is that okay by you, or would you like to ask further?
Okay, thank you. Actually, I asked this question because I remember in the paper about the optical chirality, the author claims that one should not only consider the instantaneous optical chirality. Of course, that is only for HHG, but I'm thinking,
I agree, but it's there. It's integrated there. So I do integrate it over the trajectory. You see? This is the integral of the optical chirality along the electron trajectories. So I agree. We take the integrated instantaneous chirality. So we do exactly like what they say, except we do this along the trajectory, the real trajectory. Yeah.
Thank you.
Welcome.
So we also have a question by Ven Lee. Yann, nice talk. Just a comment. You don't need a delay line detector to do 3D with VMI. We have developed a direct 3D VMI with a conventional imaging detector to obtain 3D photoelectron momentum distributions.
With a super cool camera, right?
Yes, yeah, feel free to reply live.
Oh, hi, Yann. So no, this is not the super cool camera you're talking about. Probably you have in mind the 10px3 camera, right?
Yeah.
That camera is fast, but not fast enough to do full electron time flight. So I'm talking about a hybrid, actually, detection system we have been developing in the past couple of years. Basically, you have a 2D imaging detector and coupled with some kind of a MCP pickoff from the detector directly.
Yeah.
Now you do a detection between the position and the time. So we can achieve, superb time resolution, which enables you to do the 3D.
Yeah, okay. So it can really be an enabling technology for all these things, right? Because, for example, it was a PDD to be limited in some of the measurements by the need to do tomographic reconstruction. So it's really important that all these techniques get spread and become standard. So yeah,
absolutely.
Thanks.
Absolutely.
So is there any more comment? Are there questions, comments, anything you would like to say? What we do typically is if they're not, what we do typically is we stop the streaming and we stop also the recording, because we give chance to those who would like to talk to you and ask things more informally, so that it doesn't end up on YouTube, that they will have a chance then to do so. So we're going to stop it soon. I don't see any questions. So those watching on YouTube, thank you so much for joining the Atto Fridays, for supporting our initiatives. Thank you also to Dr. Mairesse for the great talk. We're going to stop the streaming. If you would like to talk to him, or if you like to ask things more informally, hang in there, because you will have the opportunity to do it very soon. So goodbye to YouTube, and YouTube viewers will be there next Friday. Take good care of yourselves.